Yes, my presentation today is about learning, and specifically how we can improve learning. We are all learners, our students are learners, but we're also all different. And traditional learning methods usually don't take these individual differences into account. Today, I'm going to present to you one way that we can create personalized learning schedules that take individual differences into account and are solidly based in theoretical knowledge that we have from cognitive psychology. So in psychology, it's usually the big ideas that captivate us. It's the big ideas that we want to understand. We want to understand the bystander effect. We want to understand priming. We want to understand Hebbian learning. But to understand these ideas, you need a solid foundation of factual knowledge. You cannot understand Hebbian learning if you don't know what an axon is or what a synapse is. Right? So we need this solid foundation of factual knowledge. And how do people go about learning these facts? So if you look at survey data and you ask students how they learn facts, they will report using flashcards. That's their primary method. There are different variations of this, and the smartest flashcard system that is out there is the so-called Leitner system. In this method, you continuously test yourself using the flashcards that you've made, and if you answer one correctly, you'll repeat it less frequently in the future. If you answer it incorrectly, you'll repeat it more frequently in the future. And this is pretty smart, and this works really well. So if you do not have anything else, that's what you should do. Right? But we do have something else. And this is where cognitive psychology comes in. Because we have been studying human memory for more than a century. We have all these models, we have all these theories, we know a lot about learning and forgetting. Right? We have these computational models that have been implemented and they have been tested rigorously. And they can tell us a lot about how likely you are to still know something that I've taught you at some point in the future. So using these models and this theoretical knowledge that we have, we can devise learning schedules that are a lot more effective than that. So let's take a look at how that might work. So you might be required at one point to learn a whole range of brain components, right? Say to, for example, learn something interesting about biopsychology. Right? This means you have to learn a series of facts. For example, this is what a neuron looks like. Right? Now that you've learned this, this fact will be very highly active in your memory. In fact, you're still looking at it, right? So it's very, very highly active. But over time, especially if it goes away, the activation will decrease, and eventually the activation will be so low that you've forgotten what a neuron looks like. And this is the basic theoretical underlying idea. So let's take a look at how this idea might be formalized and how we can capitalize on this. So what you're seeing here is time on the x-axis, right, and the level of activation on the y-axis. So the idea here is that if I teach you a fact, one of the brain components, for example, you've now seen this fact, you've encoded it, and it's very highly active in your memory. But then at a certain point, I will take the fact off the screen, and it will still be active for a while, but then as time passes and as you start doing other things, the activation will decay. Right? It will decrease. And at a certain point, it will decrease so much that it is below a certain critical threshold, and you are not able to retrieve it anymore, so you have forgotten it. So we want to make sure that we repeat the fact, that we ask you to repeat the fact and retrieve it again before you have forgotten this. Right? So say at this moment, just before it hits threshold, I ask you, what is this thing? And you actively retrieve it from memory. You're successful. So the activation is very high again. Now you go about doing other things. Time passes. The activation goes down again. But note this time the activation will decrease at a slower rate because the additional retrieval event is basically a practice event that has stabilized the memory in your brain. So you forgot it more slowly. Again, just before you hit the threshold, we're going to repeat it. You're going to activate it again through the repetition, through the retrieval. And the subsequent decrease in activation is even slower than that. Right? And this is basically how we build stable representations. So this is the theoretical framework, and with this framework we have a lot more information than we would have with a simple correct or incorrect response that we would get on a flashcard. But all of this is just some theoretical conceptualization of activation. How do we translate this to something that we can actually observe? So the theoretical framework here suggests that there's a direct link between the level of activation and the response time on the other hand. The idea is that if something is very highly active in your memory, you are very fast at retrieving it, you're very fast at producing a response, and vice versa. So now that we have something that we can observe, we can go about making predictions, right? So I've just taught you something, and the prediction is that you're forgetting it at this rate. Just before it hits threshold, I'm going to ask you, what is this thing? And the model makes a prediction of the response time that it expects to see, right? So a relatively low response time is expected. However, at the very first trial, this prediction is going to be identical for everybody in this room. And of course, we know that that doesn't make any sense, right? Because there are huge individual differences. So this model has a very smart way of adapting to these individual differences on a trial-by-trial basis. So what happens is, it has a certain prediction for a reaction time, and then it waits for you to respond, and it records the actual observed reaction time. So let's say you are faster than the model anticipated. Your reaction time is a little bit faster. What the model then does is, it goes back and says, my prediction about the activation that I modeled internally was wrong. Right? This person forgot more slowly than I anticipated. So let me retroactively fit and adapt what this activation should have been. Then, using this updated rate of forgetting that is based on the actual observed behavior, and thereby tuned to that particular learner, we can make predictions on subsequent trials. Right? And what you note what happens here, because you reacted faster than the model initially anticipated, what happens is that the subsequent repetition gets basically postponed a little bit, right? Because the representation is more stable than the model initially anticipated. This gives you more time in the meantime to repeat other facts that you might not know as well, right? So this is a beautiful theoretical construct, but the best thing about it is, it's not only great and beautiful, it actually works, right? So we went out to a high school here in Groningen, and we tested 120 high school students. They had to learn French vocabulary for a vocabulary test that was scheduled for the next week. We took those 120 students, we divided them into two groups. The first group got the smart flashcard methods, the Leitner system, and that's what they studied with. The second group got our personalized algorithm. The study time was exactly the same for both groups. It was just the order in which the items were repeated that was manipulated between the groups. Right? So the students that studied with their flashcards, on average, got a 7. Right? So good for them, they passed the test. But the people that used our method scored on average almost an 8 on the test. Right? So this is not only a statistical significance, this is an actual meaningful, relevant difference between these groups. People score 1 grade point higher when they use our system. Right? So to summarize, using this theoretical knowledge that we have about human memory, we can create personalized learning schedules that are a lot more effective than traditional methods. Right? By building on a strong theoretical foundation, we can use the learner's responsive because they become a lot more informative than the traditional or the standard correct or incorrect responses that you would usually record. And using this information, we can devise truly personalized learning schedules. And the data shows that it works. Right? So we have the theoretical knowledge, and all of this is technically feasible. I mean, all of us have these relatively powerful computers on us all the time. Right? So I think it's time that we take the knowledge that we have in cognitive psychology and apply it in real-world settings for the benefit of everyone. Thank you very much.